I think many of you in this room know Meghan or remember her. She was one of those brave souls that joined us in 2014 when we launched the robotics graduate program for master's and PhD students. One of her cohorts is here too. So she was not the only brave soul. She was one of the brave
Just
souls.
a few, yep.
And they came with us on this wild ride that was the new robotics graduate program, where the faculty were all still affiliated with aerospace, mechanical, computer, electrical, but there was this new robotics program and try to figure out what that meant. And there were these new courses, 550 and 501, and how does this work? And so it was so great that we had some brave souls that came with us. And now as we embark on our brave souls that are going to come into our undergraduate program, and we want to have this opportunity to award Meghan for our Outstanding Alumni Award, our first ever. And we look forward to hearing your presentation.
Well, thank you very much, and thank you everybody for coming. I'm extremely honored to, be the first honoree for the Alumni Awards, even though I don't really feel like I've been an alumni for that long. But thank you for coming. So today, I'm going to be talking basically about the future, how I see the future of machine learning and robotics. And so I'm going to start with a little bit of my background, how I came to be involved in robotics and machine learning, what my path was to get there. I'm going to do a little bit of an overview of my current work and my current research. And then I'll talk about kind of how that fits into machine learning, how that fits into robotics, and what I see some of the future directions being. So just to start, before I jump into my background, I wanted to do kind of a quick overview of like an intro to machine learning and how that fits with robotics. So obviously, robotics covers a very wide range of components. There's controls and dynamics, there's perception, there's learning, there's intelligence, and you really kind of need all of these to work together to create what we call the field of robotics. Now, machine learning really kind of fits mostly into the learning and intelligence portion of robotics. And one of the very important parts for machine learning to work well is data. And data is very important, obviously, for helping robots to make decisions about the world around it. But one of the things that comes into play with machine learning that I'll talk about a little bit later is how data really needs to be accurate and specific. So a lot of the work that I've been doing over the past few years is really learning how to find good data and how to apply it correctly so that you can do really cool things with machine learning and robotics. Now, when I say accurate and specific, accurate really means we need to find the good data that looks at the questions that we're trying to answer. So how do we form our data in the best possible way to try to apply it to the questions that we have for our application that we're looking at? And then when we look at specific, we want to make sure that we're covering all the possible things that we could when we're looking at that kind of area that we want to apply machine learning to. We want to consider all the different possibilities of what a robot or a machine could encounter so that our robot can behave as best as possible in that specific environment. So a little bit about my background. I'm originally from Buffalo, New York. I attended an all-girls high school, which was a very cool opportunity for me because it first of all gave me an environment where I was really encouraged to look into STEM and look into engineering and all those possible things that I could be interested in. I had a lot of opportunities to go to a lot of different summer camps in engineering and learn really what I could be interested in going into eventually in robotics. I decided that I ended up at Santa Clara University in California, and I studied computer engineering because I found that I was really interested in the different ways that we could use data to control a robot, or we could apply it to learning about the world around us. I worked on a couple of different projects while I was at Santa Clara University, mostly focused in underwater robotics. One of the first projects that I worked on, which is the picture on the top there, is a project that we were working on in collaboration with the Monterey Bay Aquarium Research Institute. And we were trying to map the floor of Lake Tahoe to give geologists more information about kind of what was going on down there and what kind kind of data we could get from what was going on the lake floor. So I was involved a little bit in like gathering the data and then presenting it in a way that was easy for geologists to understand. The other kind of major project that I worked on at Santa Clara was called the Legacy Borehole Project. I'll just grab some water. And this project was looking at holes that were drilled in the ocean floor, mostly in the Pacific Ocean, by drilling companies probably about 50 or 60 years ago. These companies went out there, drilled these holes, and then pretty much abandoned them. And now geologists and researchers were interested in going back to them and seeing what's actually going on in these areas. Like, are there new organisms growing there? Is there like new climatological data that we can gather from there? So we were working with these researchers to design a sensor package and a whole kind of robotic system that could go into there and drop a sensor package down into the hole and then gather telemetry data and send all of that data back, display it in a way that researchers could understand and learn about. So these were some of my first introductions to kind of learning about how we needed to use data to effectively portray it, to answer some of the questions that other people in a different field might have about how we could use robotics or machine learning. So after I graduated from Santa Clara, I came here to the University of Michigan, and I entered the robotics program, as Dawn said. And I ended up graduating with a master's in robotics in 2015. While I was here at Michigan, I was very interested in looking more at what's called social robotics. So we were looking a lot at how humans and robots work together and how they can work together better to answer a lot of different questions and to help each other. So one of the early projects that I worked on, which is the picture on the top there, I designed an avatar that was basically, it would read like speeches or conversations, and people would listen to them. And then while they were listening to them, they would be wearing like a biometric signal, like sensor gatherer. And we would get data from them as they were listening to it. And then at the end, they would like self-report how they felt while they were listening to what the avatar was saying. And so we were trying to look at the questions of, is it possible to use different biometric signals to predict what people's emotions are during different like points of a conversation or like different presentations, things like that. So that work kind of folded into what my eventual thesis was, which was improved reaction and response of social robots to human emotional cues. So what this means is that we were specifically looking at how people were reacting. We were looking at the use case of a poster presentation. But eventually we wanted to expand it, that it could be applied to something, to a lot of different, analyzing a lot of different types of emotions during like a conversation or a poster presentation. So what we did was we had people basically listen to a poster presentation that was presented by this avatar. At different points, we would ask them questions and have them respond to it. And then at the end, they would self-report what their interest level was at different points during the presentation. And again, they were wearing the data collector so that we could collect some biometric signals from them. And so we were overall looking to see, are there actual correlations between the data and how people were self-reporting how interested they were in different points of the conversation, with the eventual goal being that we could maybe use machine learning to predict, like if they have these certain biometric signals, can we predict what their interest level is at the end of like a conversation or a poster presentation? So, you know, I started, both of these kind of research projects were really looking at where can we actually apply machine learning. You know, these were all very early applications of it, but it really started to show that we could apply machine learning in a lot of different ways to answer questions that researchers could have. So after I finished at Michigan, I went on to work at a company called SoarTech. This is a company that does mostly artificial intelligence for the Navy and the Air Force. And I was working on mostly natural language processing and machine learning for training and learning applications. So one of the things that I worked on one of the main projects that I was working on was a project that was looking at how robots and machines would behave in different combat missions, taking the place of humans. So the idea would be that if a person had to train for a certain combat mission, we could put agents in a simulation in place of humans controlling a different agent within the simulation. And those agents would need to act and respond as a human would, so that you could kind of simulate humans being in the simulation with them. So that involved a lot of natural language processing and speech processing, because we would basically have the human who was doing the training mission say something, maybe commanding like a plane to fly to a certain location, and then the agents would need to respond in the appropriate manner. So they would need to respond that they understood the speech command, and then they would also need to actually perform the speech command. And so this was kind of a cool application of machine learning, because it really showed that machines and humans could definitely work together to perform a common goal. I also wanted to mention really quickly, while I was in undergrad, I worked as a co-op at another space and defense company called Moog Incorporated. And mostly there, I was working on control actuation systems for tactical missiles. The two pictures at the bottom are a couple of the different missiles that I worked on. And I mostly worked on data gathering while I was there, but it was a similar type of experience as I was doing in my undergrad, where I was kind of gathering data and trying to figure out how humans could use that data to learn more about how to basically test all of the different missiles that Moog had to work with. So that was a little bit less related to machine learning, but I wanted to mention it because it was pretty cool work. I like talking about it. It eventually set the stage for what I was interested in with looking at data and machine learning.
So at SoarTech,
Yes.
John Laird is more symbolic
Yes.
level logic. So how did the machine learning get going in there?
Yeah, so I actually did not work on a lot of the stuff that John Laird had developed initially. So John Laird initially developed a language called SOAR that basically uses symbolic language to try to control different agents. Some projects use it at SoarTech, some don't. I was on all the ones that don't use it. But it's a similar type of logical reasoning application because SOAR kind of uses the rule-based if A then B. But all the projects did kind of a similar with that speech project that I was talking about. It was filling a role of if a person said A, then we need to respond in B manner. So it kind of still followed that symbolic reasoning method. Yeah, so that's kind of how SOAR is a little bit more overarching, even if we're not actually programming in SOAR.
Cool.
Yeah. So now I just wanted to talk a little bit about some of my current research. So I now work at U of M. I work in ITS, in Advanced Research Computing, which is the division on campus that controls our high-performance computing clusters. If you've ever heard of the Great Lakes Cluster, we're the group that works with that. So I work as a machine learning specialist on our scientific computing and research consulting team, which is kind of a smaller consulting team within ARC. And what we do is we work with grad students, professionals, professional labs, professors, that want to do machine learning and are interested in it. Maybe they have a lot of data, but they don't really know how to actually use machine learning. And so we can work with them to kind of do consulting about we can give them ideas about how they might be able to use machine learning. Or if they'd like us to, we can actually contract onto their team and do the machine learning for them. I wanted to mention really quickly a couple of different things that our group offers if you're ever interested. So we offer a lot of different training and workshops to learn about machine learning, about our clusters. You can find all of those online. So we offer something called the Research Computing Package. So if you are interested in actually using our high-performance computing clusters, we offer low and no-cost allocations for faculty and PhD students and reduced rates for other services that are needed beyond that. So you can always contact me or anybody in our department if you have more questions about that. We also offer something called weekly coder spaces, which is basically a weekly drop-in office hours type thing, where you can come, you can ask questions about using our clusters. If you have code that you've just got like a quick bug that you need another pair of eyes on, we offer a lot of different consulting with that. Or if you want to come ask questions about machine learning, about something new that you're trying to explore, that's a really good space for that as well. There we go. OK. So I wanted to quickly cover a couple of the research projects that I currently work on. So one of the projects that I work on is in the School of Environment and Sustainability. And we are looking at, it's basically a computer vision application where we are trying to track fish and schools of fish in videos. So this team that I'm working with has an underwater sonar camera that they've placed at the mouth of a couple of different wetland pools in the Shiawassee Natural Wildlife Preserve up near Midland, Michigan. And they want to basically see how many fish are swimming in and out of these pools, what are the species of fish, does it change at different times of the year, things like that. And they have all of these videos, and it's pretty much, it's terabytes of data that's basically running 24 hours collecting these videos. And they wanted to see if there was a way that we could automatically analyze what was going on in these videos. So they came to us and they asked us if there was a machine learning solution for answering some of these questions. So we worked with them to train and validate a machine learning model so that we can both correctly identify fish and schools of fish in images, and then also track them across the frames so that we don't like count one fish as like 10 different fish, obviously. And then we also do some post-processing to determine the size of the fish, which can give clues about what the species might be. Unfortunately, since the video is sonar, it's not granular enough to actually be able to see what the species of fish is, but the size of the fish can kind of give us clues about what that might be. And then we can also identify the schools of fish, and we can do sizes on the schools, which can give us information about how many small fish might be in the schools. We also calculate the directionality of fish, which gives us an idea of like how many are going in or going out, which can eventually give us clues about what the condition of the different wetlands is and other questions that they might want to answer with that. So like I said, this is a collaboration with USGS and the SEAS graduate team over at the School of Environment and Sustainability. So it's been a really cool like application of machine learning. You know, we're using a ResNet, a convolutional neural net, to basically just kind of apply it to these videos that we have.
So were they trying to count these by hand before
Yes.
you guys came on board?
So there are a couple of different methods that you can use for counting fish. They're called, you can do something called gill netting, which is where you basically take like a giant net and just put it in and try to drag it through, and then you count the number that you pulled up and do extrapolation from there. There's a couple of other methods that they use. I'm not super familiar with all of them, obviously. Yeah, so they were kind of trying to use these estimation methods out in the field to answer some of these questions. And they wanted to see, you know, is there a better way? We have all of this data. What can we do with it? Yep.
So do they give you like the labels for the sonar imagery?
Yes. So one of their major jobs is to create training data for me. So they have to identify videos that they think have a lot of like good fish and schools in them, and then they go through, label them for me, and then I use all of those to create their model for them, and then they have like all of their videos that they're actually interested in that they can then run through the model and get answers from. So another project that I'm working on is in collaboration with the med school and with CSCAR here on campus. And this is a study, it's called the kidney morphometry study. And we're basically trying to train and validate a convolutional neural net to identify and morphometrically assess large areas of kidney tissue. So what this team has is they basically have a lot of scans of people's kidneys. And within your kidneys, there are a lot of different structures. Some are called glomeruli, some are called tubules, there's some blood vessels. And all of these play a different part in like filtering waste and then eventually getting rid of waste from your kidneys. And they wanted to see if there was a way to automatically identify those structures in the kidneys and then also be able to assess the condition of them so that that could kind of give them clues about what condition your kidneys are in. If you're at risk for maybe developing kidney disease in the future, it can answer some of the questions like that. So I've been working with them to fully identify and segment and classify these glomeruli and other features. And then we're also using a Java program called ImageJ which does quantitative automated morphometrics, which basically means that it takes all of the identification info and turns it into like numbered data that gives data about like where the glomeruli or other structures are located, how far away they are from each other, like what depth they are at the kidney, and that can answer some more medical questions if they're interested in. So again, this is just a very cool application of how you can take a machine learning model that really already exists and just apply some of your own training data and answer some novel questions. As you can see, I've worked on a lot of different projects that use machine learning in a lot of different ways. So obviously, machine learning is becoming prevalent in so many different fields. And it's really important to kind of recognize how machine learning is going to play a role in robotics in the future. It's definitely the case where there has been a lot of new and novel development of machine learning algorithms in the past maybe 5 to 10 years. But we're really more getting to the point where there's not as much development that needs to happen, and it's more that there are new and novel ways to apply machine learning. So that's where a lot more of the innovation can come from when you're looking at machine learning. Now, obviously, machine learning can also encompass a very wide range of research. As you can see, we've done computer vision, natural language processing. You can do reinforcement learning to apply it to different robots. So there's really just a lot of different ways you can think about how machine learning can answer questions and what you want to do. So kind of where I see the future of machine learning with robotics going is when you're thinking about robots, it obviously requires, interacting with robots is eventually going to require machine learning because you eventually want robots to behave how you would expect a human to behave. And what machine learning does is it teaches a computer, a machine, a robot, basically how to think how a human thinks. So, as robots are becoming more integrated into our lives, we really need to find a better way to effectively interact with them. So machine learning can answer a lot of these questions. A lot of people talk about the future of robotics as like robots are going to take over and, humans are going to be out of jobs. But I really think that the eventual goal of robotics is really more that humans and robots need to work well with each other. And so using machine learning to teach robots how to work with humans and how to behave how humans expect them to can really kind of help that drive of robotics forward and can help the innovation of machine learning in general. So with that, I just really want to thank everybody again for having me this weekend, especially thanks to Don Tilbury, the entire robotics department, for hosting me. If you have any questions, if you want to contact me, all of my contact information is there. You can also look into our general advanced research computing. You can look on our website to find out more about what we offer and all the information about our Coder Spaces drop-in time if you have any questions about that. But again, thank you again for coming, and I can take any more questions if people have them.